I welcome you all to CIT Quantum Hackathon 2022 workshop series sponsored by IBM Quantum as a part of Qiskit Fall Fest. With this, I'm extremely pleased to welcome our chief guest and the speaker of the event, Dr. GayathriDevi, Assistant Professor at CIT, on the topic of Qiskit Backends. She has completed her PhD in multicast routing algorithms in mobile ad hoc networks, and she is also a IBM certified associate developer quantum computing using Qiskit. And she is a platinum level Qiskit translator 2022. And she also research on IBM Qiskit localization to Tamil language. With all these introductions, I'm pleased to welcome you, ma'am. This session is all yours now.
Thank you, Shivsuma.
Yes, ma'am.
Good afternoon.
Good afternoon, madam.
My screen is visible.
Yes, ma'am.
Yes, ma'am.
Okay. So my topic is Qiskit Backend. I'm a Gayathri, IBM Certified Associate Developer and Assistant Professor of Department of Computing, CIT. So agenda, we are going to see about the introduction to backends and sample code and conclusion. So before going to the backend, I introduce the Qiskit. So Qiskit is a open source SDK for working with the quantum computer at the level of pulses, circuit, and application module. We can run this Qiskit library locally with the help of Python, or we can go for the remote environment uh, using this Q Lab, Quantum Lab. So I open my environment as locally. So I go for Anaconda Navigator. So in Anaconda Navigator, we have a Jupyter notebook. I launched this Jupyter notebook. And this we create a new file, or we can open the existing one. I open the existing one. So this is my existing notebook. In this notebook, you should install the Qiskit using this pip command, pip install Qiskit. So I already installed this, so no need to install that again. So this is the environment where we execute our quantum circuits. This is a local environment. When we go for the global environment, we have IBM Q. So this is IBM Q. So when I sign into this IBM Quantum Lab, we can use the IBM ID, or we can use the Google account. I use this Google account. So we have two options. One is the IBM Quantum Composer, another one is the IBM Quantum Lab. In IBM Quantum Composer, we have icons to draw a circuit and run that circuit. So I already created one circuit using this icons. So we can delete it and we can go for a new one. So we can delete this. Okay, I add Hadman gate and qubit 0, and then I add C0 gate and 0 comma 1. Then I add the measurements. Okay, so the bottom of the screen gives the probability, state vector visualization, and Q sphere visualization. Okay, so this is a quantum composer. When we move to the quantum lab, we have a Python notebook. So in this, we can create a new file using this button, or we can open the existing one. So on the left side, we have existing files. So I open the existing files. So this is a remote environment. Okay. So this is a base for Qiskit. So we move to the backends. So backend provides the execution environment for our quantum circuits. In Qiskit, backend refers to the things on which the quantum programs actually runs. The backends may be a simulator or a real devices. To set up a job for a backend, we need to set up a corresponding backend objects. So the core component of Qiskit backend frameworks are provider, backend, and job. So provider accesses the backends and provides the backend objects. Backend runs the quantum circuits. So job keeps track of submitted job. So this is a Qiskit workflow. We design a quantum circuit, we compile or execute that quantum circuit, which gives the Q object, that is quantum object. To compile and execute the quantum circuit, we need the backend support. So that backend is provided by the provider. Okay. So the Q object is run through the backend through run method. So it gives the job. So from the job, we get the results. Okay. So the provider is the initial point in this flow. So provider is an entity that provides the access to the group of different backends. It interacts with the backends. We have two methods. One is the backend of, it returns the all backend objects known to the provider. The next method is get backend of name. It returns the named backend. So in, some of the Qiskit providers are AIR, Basic AIR, and IBMQ. AIR and Basic AIR provide access to the several simulators that are included in Qiskit and run on a local machine. IBMQ implements the access to the cloud-based backends, such as simulators and real devices, which are hosted on the IBMQ. So to get the list of backends from the local using our R simulator, R API, we need this code from Qiskit. From Qiskit, we import the R API. We iterate that backends, and in each iteration, we print the backend name. So the output is QSM simulator PY, state vector simulator PY, and unitary simulator and Clifford simulator. To get the instance of backend, we need this backend equal to r.get backend of QSM simulator. So this is R API. Next one is the basic R API. So here the basic R from Qiskit, we import the basic R API. Then we iterate the backends and print the backends. Okay, the output is Qiskit simulator, state vector simulator, then unitary simulator. To get that instance of that backend equal to basic r dot backend of QSM simulator. Okay. So using IBMQ, we can get the backends. So for that, we importing the standard Qiskit libraries. After that, we load the uh, IBM Quantum account. That is provider equal to IBMQ dot load account of. After that, we give the providers. IBM Q dot providers, or it lists the IBM Q and QC hyphen Spring hyphen 22 hyphen 2. These two are the providers. So from this provider, we get the backends. So provider equal to IBM Q dot get provider of hub equal to IBM hyphen Q. Then provider dot backends of, it lists the um, available simulators and real devices inside that IBM queue. Okay. To get the real devices, we have to set the two parameters. That is provider dot backends of simulator equal to false, then operational equal to true. So it gives the real devices. Okay. Okay, that's all about the providers. Then backends. Backends represents either a simulator or a real quantum computer. It is responsible for quantum circuits and returning results. Input for this backend is quantum object, which is the output of the compilation process or execution process. This process returns this backend returns the job object. So backend use the following methods: run of queue object, which submits the queue object for running and returning a job, configuration of. So returns the backend configuration dictionary, which describes how the backend is configured, such as its topology or a native gate set. Then properties of a dictionary of a backend with the specific properties. Name of the backend. Status of a dictionary of a backend status, such as how many jobs it has queued, like that. Then IBM Q backend uses the following methods: jobs of limit, skip, status, and DB filter parameters. So it returns the list of job, index from skip, and end at limit. Okay. So then retrieve job of job ID. It returns the job matching with the job ID. So getting a least busy devices with 5 qubits, we need this code and IBM Q. From Qiskit provider.ibmq, we import the least busy method. Then we need a filter and lambda function to get that least busy devices with 5 qubits. So small devices equal to provider.backends of filters equal to lambda x colon x dot configuration dot n qubits equal to 5. So our real devices should have the 5 qubits and not x dot configuration dot simulator. So it should not be a simulator, it should be a real device. So it returns the list in a small devices. That list is passed to the least busy method. It returns the least busy device. So here the least busy device is IBMQ Manila. So in the configuration page, we have different properties. So here the simulator value is a false. So it is a real device. So next is a job. Job instance can be viewed as a ticket for a job that has been submitted. They reveal the state of the execution at the specific point, such as whether the task is queued, executing, or failed. They are also give the user control over the job. They have the following methods. Result, this is a block call that returns a result object. Status returns the job's status object. Cancel attempts to cancel the job, returns true if successful. Backend backend instance which creates the job ID, a string of the IBMQ API uses to identify that job. Then IBMQ jobs can also supports the following methods: creation date of the date the job was created, queue position of the an estimate of position of the job on the server queue, error message of a message from API if the error was encountered with the job. So this is a sample code for creating a job. First, we create design a circuit. The circuit is GHZ gate. GHZ gate. So from Qiskit, we import the quantum register, classical register, quantum circuit. We import the basic AR API and execute. So we get the three register, quantum register. We store it in QR, and CR is for the classical registers. So classical register of 3 returns the 3 classical register. So QC equal to quantum circuit of QR comma CR. So it creates the quantum circuit with 3 quantum register and 3 classical register. Okay, in the circuit we add Hadamard gate, H of 0 at Q bit 0, and CX of 0 comma 1. So this is a C naught gate with control 0. Control is a Q naught bit, and target is a Q1 bit. So next is another C naught gate on 0 comma 2. We measure this values and we draw the circuit using this draw command. So in this draw command we give MPL. MPL is a matplotlib library to draw the circuit. So this is a circuit of this code. So this is ZHZ gate. So in this we have a measurements. In classical we have a 3 classical registers, 3 quantum bits and 3 classical bits. So after creating this quantum circuit, we go for the backend. So backend equal to basic AR dot get backend of QSM simulator. So the basic AR API returns the backend with the name QSM simulator. So this object is used for execute the designed quantum circuit. So job equal to execute of QC. QC is already designed quantum circuit. Here backend is a QSM simulator, and shots equal to 100. Here shots denotes the number of times the quantum circuit should be run. So this execute returns the job instance. So the result equal to job dot result of, we get the results from the job. Count equal to result dot get count of. So we get the counts from that results. So how many zeros and how many 0 state and how many 1 states. That is the count. So we print the counts. 1 occurs 51 times, 0 in 49 times. So finally we plot the histogram for this counts. So this is our histogram. So ZHZ state as a 1 by root 2 of 0 plus 1. So next is a state vector simulator. Here we design the same circuit without the classical register. So QC equal to quantum circuit of 3. Then QC dot H of 0. We add the H Hadamard gate at quantum bit 0. Then we add the C naught gate and at 0 comma 1 and C naught gate at 0 comma 2. We get the basic AR dot get backend of state vector simulator. We run the designed circuit using execute of QC1 comma backend comma shots equal to 1024. So this is a default value for the shot. if we not mention, so the result equal to job dot result of, then we after getting this result we get the state vector from the result. This is the one of the representation of the result. So previous representation is the histogram. This is the state vector. So state vector gives the combination of all the bits positions, that is state of the all the uh, bits. Okay. So here we have eight combinations. So because we take three quantum bits, so 2 power 3 equal to 8. So we have 8 combination. So first 000 has the 1 by root 2 value, and 111 has the 1 by root 2 value, because this is an entanglement state of 3 qubits. So next is a real backend and job monitor. From Qiskit dot tools, we import the job monitor to monitor to get the status of the job. So here the provider is the IBMQ dot get provider of the backend equal to provider dot get backend of named backend IBMQ Qto. So we execute this circuit, already designed circuit. C has already designed circuit QC with this backend. Then we apply this job to job monitor. Here the job status is queued. So the real device is busy, so the job is in queue. So so that we don't get the result. If the job is run successful, so this job has run successfully, we get the counts. We can get the counts, and we plot the histogram. Here we have a histogram output. In this output, 000 occurs 48 times and 111 occurs 40 times. So the remaining states have 11 times, 18 times, 23 times, 9, 13 times, and 32 and 31. Because of it as a real device, it added the noise. So we have a small amount of noise. So when we move to the IBMQ lab, so this is our IBMQ lab. So I open already existing notebook. We show the result of this design circuit. So we imported a standard Qiskit library. So to run this cell, we have this button, or we can give Shift plus Enter to run the cell. So when I running the cell, it loaded the IBM quantum account details. After that, I design a circuit. So this will give the circuit design. Then I use the QSM simulator as a backend. This is from our basic AR API. So this circuit is run with the shots 1024. We get the results. From the results, we get the counts, and we plot the histograms. Histogram for this. So this is a histogram. Then I use the state vector simulator. So again, I redesign that circuit without any classical register. So I run this. Then backend is a state vector simulator to get the state vector. So we execute that design circuit QC1 with the backend state vector with the shards 1024. So after executing that statement, we get the job instance. So from that we get the results. Results dot get state vector gives the state vector representation. So this is a state vector representation. So using the state vector representation, we can give several visualization. So this is a plot state Q sphere. This is one of most important visualization. It gives the entangled state 0, 0, 0 and 1, 1, 1. At the same time, our circuit is in half 0, 0 and half 1, 1, 1 state. So next is a block sphere representation. So here we don't have any pointer in this block sphere because it is in entangled state. So next is a state city representation. The state it is. Okay. So using our state vector, we can give several visualizations. So next is unitary simulator. We get the unitary simulator from basic R API. We execute the design circuit with this backend and we get the results. So this is our unitary backend. Here get unitary of decimal equal to 3. So the decimal points are delimited to three positions. Okay. So next is our real device. So for the real device, we go for the Ibmq API. So we for monitoring the job, we need this job monitor. So this is from Qiskit tools. So provider equal to Ibmq dot get provider of. So backend equal to get provider. Backend equal to provider dot get backend of name Ibmq hyphen qto. So we execute this circuit with this backend real device. So we monitor the job. So here the job status is queued so that we don't get this result. So it is in queue. So the real device is busy, so the job is in queue. Okay. So for getting the least busy devices, we have this code. So this is a standard library importing and providers and get providers. So this is for getting the real devices. So the simulator equal to false. So getting operational devices with the qubit is greater than or equal to 10. We need this lambda function. So here x dot configuration dot n qubit is greater than or equal to 10 and not x dot configuration dot simulator. It should be a real device. It should not be a simulator. And x dot status dot operational equal to true. It should be a operational one. So here the list is empty. Now this list is empty. To get the least busy devices with the quantum bit 5, so we import the least busy method from Qiskit provider.ibmq library. So small devices equal to provider dot backend of filters lambda x colon x dot configuration dot n qubit equal to 5 and not n dot configuration dot simulator. Then it returns the list. The list is given to the least busy devices. So when I run this, so it's take some time to load. It lists the backends. Then it lists the operational backends. Then lists the empty list for the operational device with the qubit greater than or equal to 10. So it displays the real device with qubit 5. So the small device is Manila, sorry, Qto, least busy device. Okay, with the configuration properties and error map and job history. So you can see this. Okay. So in this configuration properties, simulator is false so that it is a real device. Okay. Any doubt on this? So this is a way for running our quantum circuits. We can either use a local machine or we can go for a IBMQ. So then in conclusion part, Qiskit interfaces contain the providers. Provider lists the backends. The backends accept the job request that contain one or more circuits to be run at a specified time of shots. Um, Depends on the simulator or a real device, we get the different visualization such as array representation, state vector representation, and unitary representation, etc. So these are my references. Thank you.
That was a wonderful session, ma'am. Participants, do anyone of you have any queries? Just feel free to ask your queries here. I think there is no doubts from the participants, ma'am. So we have arrived at the end of our session. Can you hear me, ma'am?
Yes, ma'am.
Yeah. So we have arrived the end of our session, and I once again thank and extend my gratitude to Dr. GayathriDevi, ma'am, for joining hands with us. I would like to thank ma'am Manjula Gandhi, ma'am, for leading and supporting us throughout the process. I thank each and every one of you for joining the session. Stay tuned in our Discord server for announcement and updates. Recorded video of this session will be posted in our Discord server. As always, feel free to post your doubts and queries in the Discord server. We are always here to help you guys. Timing and link for the further sessions will be circulated throughout the Discord channel. Thank you.
Yeah, I thank Dr. Manjula Gandhi ma'am for giving this opportunity, and I thank our CIT management, faculty members, and friends and family for learning this journey, learning journey. So all the best for organizing team and hackathon participants.
Thank you,
Thank you,
ma'am.
ma'am. And also, a feedback form is posted in the chat box. So do fill the feedback forms, participants.
I would also like to thank Jairani ma'am and Manju ma'am for extending your support and joining us. Thank you, ma'am.